Hi, today I want to tackle one question. As this mysterious number I, the square root of -1, seems so completely useless, I just have to wonder how on earth could complex numbers ever be useful. But it turns out I does turn up for signal processing, like in your phone, or when you study the smallest particles in physics. Even when dealing with prime numbers and the famous $1,000,000 equation, complex numbers show up. But understanding how they show up? Well, that takes some time, but that's anyway not our goal. We would be satisfied with even one simple example where complex numbers are the hero. One elegant problem, which initially couldn't be further from a complex solution, and that's exactly what I have for you today. It starts out with simply counting certain groups of people, but will lead to us even longing for complex numbers to exist. And soon after, bam, problem solved. And in fact, what we will be doing is even related to the $1,000,000 problem I mentioned, the most famous unsolved problem in mathematics, which is about prime numbers and how they can hide in one single equation, an equation worth $1,000,000. So let's start by tackling this counting problem, and you tell me if initially you can smell the square root of -1 hiding somewhere. Say you are a teacher and you have to pick some of your students to form a team for a competition. While you think about all the different teams you can form, you get the extra information that the number of students in your team has to be divisible by 3. So this team of 5 students is not allowed, as 5 is not divisible by 3. But if you add one more member, we have 6 students, which is divisible by 3. So in this example, when there are 8 students to choose from, the team can only consist of 3 or 6 students. It turns out there are 56 possible teams of 3, and here all of them are. Instead, if you want a team with 6 members, there are 28 possible teams. Again, here they are. So 56 teams of 3 and 28 teams of 6. Also, there is this one additional choice of not choosing any student at all, as 0 is also divisible by 3. So in total, when choosing from 8 students, there are 85 different possible teams. Since you are completely overwhelmed from so many choices, you procrastinate and wonder about the general case. If I had n students to choose from, then how many teams divisible by 3 could I form? That's it. That's the entire problem, and I think you would agree that so far nothing hints at complex numbers. So let's get a feel for the problem by considering the small cases. If we only had 4 students to choose from, there would be 4 possible teams of size 3, and again the one empty team, so 5 in total. For 5 students, there are 11 such teams. Starting from 6 students, that's the first time we have to consider teams of size 6, as 6 is also divisible by 3, and in total there are 22. So we have computed some answers for n, and it's just a curious question to find out how this sequence continues, or in general to find a formula for it. And again, no complex numbers inside at all. So, where to begin? Well, in general, we are interested in how many ways there are to choose k students when given n students. Say for instance, we have 4 students and we want to have teams of 2. We could either pick the first 2, or the last 2, or blue and black, and so on. In total, there turn out to be 6 possible teams. Counting the number of subsets is common in mathematics, so there's a special symbol called the binomial coefficient. So there are 6 ways to choose from a set of 4 elements, exactly 2. One could write it like this and say that 4 choose 2 equals 6. Now what about choosing 3 students from 4? Well, there are now 4 such teams, so 4 choose 3 is 4. Next, 4 choose 4 is 1, as there we simply have to pick every player to get a team of 4. Similarly, 4 choose 0 is also 1, since we get it only by not choosing any player. And last, as there are 4 teams of 1 player, 4 choose 1 is 4. So we now know the number of possible teams when choosing from 4 players. In the correct order, there are 1, 4, 6, 4 and 1 such teams. And let's remember this sequence. It is going to make a surprising reappearance later on. Using these binomial coefficients, our problem can be rewritten. For instance, for n equals 8, these are now just the binomial coefficients 8 choose 0, 8 choose 3 and 8 choose 6. And we are interested in their sum, so choosing every team size divisible by 3. For 9 players, we will count the teams of 0, 3, 6 and 9 players. for 10 players to choose from, we will also count the teams of size 0, 3, 6 and 9. So in general, we compute the sum of all binomial coefficients such that the team size is divisible by 3 and does not exceed the total number of students. This has transformed the counting puzzle into a summation problem. Great, but I have a question. Why are these called binomial coefficients? Well, that's because they appear when expanding powers of binomials, an expression with two terms. Say we have a binomial like 1 plus x and we raise it to some power, but now want to expand everything to get rid of the brackets. This can be done by multiplying each of the terms of the first bracket with each of the second and so on. And when we add up all these combinations, we are done. This sounds tedious, so let's do it only once and maybe we notice something. So we start with multiplying all the ones, which is 1. Next we take the x from the first bracket and the other still 1 and get simply x. Next the combination with the x in the second bracket, then the combination with two x's which gives an x squared. And after one is done with all the rest, we can combine all the same powers and simply get this. But wait, 1, 4, 6, 4, 1, these are precisely the binomial coefficients from before. So it seems that if we take the power, in our case 4, we get the binomial coefficients corresponding to counting subsets of 4 elements. For instance, there are 6 groups of 2, and the 6 is indeed right here. In fact, it is the coefficient of x squared, so the number that x squared is multiplied by. So this explains the word coefficient in binomial coefficient. But the obvious question is, why on earth should this be true? Like, why do these coefficients show up? For instance, why did we get 6 sets of 2 and also 6x squared? Well, let's investigate how we arrived at those 6x squared. For the first x squared, we took the x's here and otherwise the ones, and multiplying gave x squared. The second, we took the x's here and the other ones. For the third, we took them here, and in general, for each pair of x's we can choose, we got an x squared. So from those 4 x's, we had to choose 2. And well, the number of ways we can choose 2 x's from 4, by definition, is exactly 4 choose 2. This is the reason there were 6x squared. The same holds true for x cubed. Choosing 3 of the 4 x's is the same as choosing a group of 3 people, so 4 choose 3. And similarly for the other powers. And just like that, we have discovered the binomial theorem. It states that when expanding 1 plus x to the n, instead of multiplying out, we can simply write all the powers of x, starting from x to the 0, which is 1, up to x to the n, and in front we have exactly the binomial coefficients. Now let me just highlight how completely crazy this result is and tell you about this $1 million problem. Say we are interested in working with some sequence of numbers. For instance, the binomial coefficients 10 choose 0, 10 choose 1, and so on. Right now, we have no clue what they are, so how could we possibly work with them? But we do know, if we take those numbers, that we are far too lazy to compute and plug some powers of x in front, we can simplify the sum using our formula. So these coefficients, which again we don't know, hide inside this very elegant and simple form. This closed form can be viewed as being generated by our unknown numbers. Our numbers were used to generate this function, and also using this form, we can recover or generate all the numbers again. Hence it is called a generating function. One could say a generating function is a device somewhat similar to a bag. Instead of carrying many little objects detachedly, which could be embarrassing, we put them all in a bag, and then we only have one object to carry, the bag. And our mission, should we choose to accept it, is to infer information about the underlying numbers by interrogating this closed form. In our case, we want the sum every third binomial coefficient. And what might help somehow is plugging in different values for x. So at this point, I just have to pause our problem for a moment and add that this is essentially where the $1 million problem about prime numbers emerges. Say we have our beloved prime numbers and we want to investigate some of their properties, for instance, how common they are. So as before, we have a sequence of unknown numbers, but maybe we can put them all in a bag somehow. It would be great if we could just multiply them with powers of x and for some magical reason find a closed form for this infinite sum. But unfortunately, it's not as easy, but close. we can take the logarithm of 2 divided by 2 to the x minus 1 plus the logarithm of 3 divided by 3 to the x minus 1 plus log 5 divided by 5 to the x minus 1 and so on for each prime number. Granted, it isn't as pretty as it could be, but it is generated precisely by the prime numbers. And remarkably, this infinite sum can be expressed in a closed form. And this function right here is the so-called Riemann-Zeta function. And here is its derivative. It is defined as this infinite sum, or something very close to it. And that's insane. Those tricky prime numbers can all be put in one single bag. And it turns out that understanding the distribution of prime numbers boils down to finding all x such that this expression is infinite, which happens when the denominator is 0, which is the million-dollar problem. And again, most of these solutions are in fact complex, because why wouldn't they? In case you are interested, I have already made a video about how this relation between the zeros and prime numbers works, link in the description. And our problem about counting groups is somewhat similar. While prime numbers hide in this bag, our binomial coefficients hide in this much more simple expression. So no million-dollar prize for us. So, to show how complex numbers can turn up out of nowhere, we went from counting groups divisible by 3 to the binomial theorem, which is a generating function. And a similar generating function of prime numbers leads to a million-dollar problem. So let's see how our generating function can be useful in our $0 problem. To recap, we have a formula for the sum of every binomial coefficient with these additional powers of x, but would need the sum of every third binomial coefficient. So essentially, we want 2 out of 3 terms to just magically disappear. And this is where plugging in values for x can be useful. We want every third factor to be 1 and every other to be 0. But right now, there is no suitable x. So, to get a better intuition for the problem, we should start with 2 easier problems. First, can we get a formula for summing every binomial coefficient, so without those x's? And second, can we get a formula for the sum of every second binomial coefficient? For this one, negative numbers will show up, and for the third, complex numbers make their appearance. So first the simple one. We want to know what the sum of every binomial coefficient is, maybe using our binomial theorem. Well, we need to just get rid of these x's and we will be done. So let's just set x equals 1. Now all the powers are 1, so they vanish. And just like that, we get that the sum of all binomial coefficients is simply 1 plus 1 to the n, also called 2 to the n. That's it. Let's quickly think about what that actually means. We are taking the number of teams with 0 players, plus those of 1 player, plus those of 2, and so on. So this is the total number of all possible teams, without considering their size. For instance, for 6 students, there turn out to be 64 possible teams, and indeed, that's 2 to the 6. Now, how about summing every second term? This would correspond to being only interested in teams of size 0, 2, 4, simply an even number of students. So all even powers of x should be 1 and all the others 0. Well, there isn't such a number, so what could we do instead? Maybe all of the even powers could be one number and the odd powers some other number. This way we might be able to separate every other term. Well, we are always multiplying from one term to the next with x squared, which shouldn't change the number. Hence x squared should be 1. And there indeed is a number that squared gives 1 and isn't 1 itself. And its power changes between two numbers, namely -1. Every even power of -1 is 1, and every odd power is -1. This allows us to separate the even and the odd teams in the sum. When we set x equals -1, we get a plus in front of the even teams and a minus in front of the odd teams. Now, there's a simple way to get rid of the odd teams completely. First, we can use the formula from before with the sum of all coefficients. And if we add these two lines, then every second coefficient cancels perfectly, while the others are 2. Now we can simply divide everything by 2. This gives a formula of the sum of every second coefficient. And here, this 1 minus 1 to the n, that's just 0. And just like that, 2 to the n divided by 2, or simply 2 to the n minus 1, is a formula for the number of even teams. For a quick check, if we have 6 people, there turn out to be 32 possible teams with an even number of players, which indeed is exactly 2 to the 6 minus 1, or 2 to the 5. So here we are. When we wanted the sum of all coefficients, we wanted all powers of x to be 1, hence x equals 1. When wanting to separate every second coefficient, we needed an x with x squared equals 1. And now we want every third power to be the same, hence an x with x cubed equals 1. And just like that, we are basically forced to find such a number, even though finding it is a little complex. So let's quickly introduce complex numbers and their necessary properties. First, there is this number I that when squared gives -1. Now any complex number is I times a real number and plus another real number. The part not involving I is called the real part of the number, and the second one is its complex part. Adding and subtracting complex numbers is simple. You just add or subtract their real and complex parts individually. Multiplying is similar. You just expand the product as is usual with brackets. Additionally, whenever you find an I squared, you can replace it by -1, as I squared is -1 by definition. Now, what turns out to be quite helpful is plotting complex numbers in a plane. We can set one of the axes to be our real axis and the other to be our complex axis. For instance, we would plot the number 1 plus 3i right here. It is 1 unit in the real direction and 3 units in the complex direction. Plotting complex numbers in a plane isn't only pretty, but operations like addition and multiplication can be visualized neatly. First, when adding two complex numbers, such as 1 plus 3i and 2 plus 2i, we get the result by simply stacking their vectors together. This is because adding this way results in precisely adding their real parts, or x components, and their imaginary parts, or y components. But the real beauty lies in multiplying complex numbers. Now, there are two things that turn out to be always true when multiplying. First, if you measure the two angles of the numbers to the positive x-axis, then their product will have exactly their sum of the angles as angle. And second, we need to measure the distance of the initial numbers to the origin, so this length, which is also called the absolute value. It turns out their product will have precisely the product of their lengths as length. If we follow this construction, we indeed again end up at -4 plus 8i as before. And that's all you need to know. When multiplying, the angles get added and their length to the origin gets multiplied. Now, it is not at all clear why these rules are true, and the reason is indeed quite involved, so maybe a topic for another day. For now, we will just take it as a fact. And for us, this rotation will be key to solving our problem. But we will focus on our numbers that lie on this unit circle. This means their distance to the origin is 1. For such numbers, we don't have to worry about their length to the origin when multiplying, so multiplying such two numbers is as simple as adding their angles without having to worry about their lengths. By the way, this also gives a new way of seeing the powers of -1. If we multiply -1 with itself, we simply add its angle, the 180 degrees, to itself. Since we get back to 1, we see that -1 squared is 1. If we multiply by -1 again, we again add that angle and are back at -1. So -1 cubed is -1. And this adding of 180 degrees for each power continues on and is just a neat way of seeing the powers of -1. So in general, when we have a number x, then x squared, x cubed, and so on can just be found by adding the angles of x again and again. So our goal is to find an x with x cubed equals 1. Well, we can just play around with x, as we know that x, x squared, and x cubed are just equally spaced points along the circle. And we want x cubed to be 1, so right here. And before we know it, we indeed have this x right here, such that x cubed is 1. As always, the angle to x is the same as the angle from x to x squared, and again to x cubed. This means each angle must be exactly a third of 360 degrees, so 120. So this number right here is quite special, and we should give it a name. Let's pick the small Greek letter omega. So omega is here. Omega squared has double that angle, so it is here. Omega cubed is at 1, which is precisely what we wanted. Also, one can go on. So omega to the 4th is the same as omega. Omega to the 5th is omega squared, and so on. So all powers of omega are one of these 3 points and go round and round the circle. Now, I have to mention that using a little Pythagoras, we can find the precise value of omega. It is -1/2 plus square root of 3 divided by 2 times I. However, this precise value actually isn't important. So coming back to the question, which numbers cubed give 1, we have omega as a solution. And well, 1 itself is also a solution. But something seems missing. What about omega squared, which is down here? If we square it, we end up at omega to the 4th, which is just omega, and if we cube it, hey, we are back at 1. So omega squared also is a valid solution. And as x to the 3rd equals 1 is an equation of degree 3, there indeed should be 3 solutions. So great! Let's plug omega into the generating function. On the right, we get the linear combination of all those powers of omega. These can be simplified a lot, as every third is just 1, every other third is just omega, and the others are omega squared. So at the very least, all those terms that we are interested in finally all have the same coefficient, namely 1. But what now? Well, what happens when we plug in omega squared, which is the other solution? Again, we can simplify a lot, and every third coefficient is 1. But whenever we previously had omega, we now have omega squared, and also the other way around. But what is omega plus omega squared? Well, let's look at our circle. If we add these numbers by combining their vectors, we get the point -1. Hence omega plus omega squared is -1. So as before, let's add these two equations. Now, the numbers we're interested in have 2's and the others have -1's. So once again, we have separated the important binomial coefficients from the rest. And how can we get rid of the others? Well, we simply add the formula from before for the sum of all coefficients, so they cancel perfectly. And after dividing by 3, we arrive at the remarkable formula 2 to the n plus 1 plus omega to the n plus 1 plus omega squared to the n divided by 3. This is the formula we were looking for. Before, when we computed some of the first terms, this was the underlying formula. This is the answer to how many groups divisible by 3 there are. And it's remarkable that complex numbers show up, isn't it? But also, right now, this formula is sort of hard to understand. I mean, what even is this stuff right here? Well, it can be simplified a lot. First of all, it turns out that 1 plus omega lies right here, again on the unit circle. Also, this angle here is 60 degrees, and 1 plus omega squared lies just down here. We should probably give them new names. For instance, the Greek letter tau, or tau bar on the bottom, as it is just tau flipped along the real axis, so it's complex conjugate. If we square them, they are here. Cubing them gives -1 for both, and so on. So as you can see, they are always their mirror image. Now, what about their sum, as this is the one thing that we are interested in right now? Well, if we add them by stacking their arrows, we always end up back at the real axis. So if we want to compute the precise point, we can focus on adding only the x-coordinates of both arrows, so they are real components. These are always the same for both arrows, so we can just multiply one of them by 2. So 2 times the length of these gray arrows, or 2 times the real component of tau to the n. And how do we get this real component if we are on the unit circle? Well, this angle right here is 60 degrees, or 120 degrees for tau squared, or 180 degrees for tau cubed. So in general, 60 degrees times the power n. In geometry, this is known as the cosine of that angle. So the cosine is by definition the value at the x-axis. Plugging this in, we get that this tricky part is just 2 times the cosine of 60 degrees times n. That's it. This is the final solution to our problem. This simple counting problem about groups divisible by 3 has this formula as an answer. And using this formula, we can compute the numbers of these sets very efficiently. And note, this 2 times cosine term just cycles between being +2, +1, -1 and -2. Just remarkable. So not only did complex numbers show up, but in fact trigonometry. And I think you would agree that in the beginning nothing at all hinted at this. This is just math being crazy. So this is my favorite example of how complex numbers can show up completely out of nowhere and save the day. And this isn't an isolated trick. In general, whenever you have some periodic behavior, like wanting every third coefficient of a generating function, or maybe even something with prime numbers, complex numbers are not just a possibility, they are often the simplest and most direct path to a solution. They are the universal language for rotation, even when the problem seems to be standing still.